So welcome. My name is Terrence Barkin. I'm the Executive Director of the Graphene Council, and we're hosting today's webinar, which will be presented by B Energy on graphene production method that they have and about their company. The Graphene Council, if you're not familiar with us, is a global trade and professional body that reaches more than 35,000 material scientists and professionals with an interest in this material. And that includes researchers, graphene producers, and people who are using graphene in their products and materials every day. We're very pleased to introduce B Energy, which is a startup company out of the University of Calgary. And we have the two founders of the company, Ashutosh Singh and Ted Roberts, who is a co-founder of the company, is also a professor at the University of Calgary. And so again, B Energy is a member company of the Graphene Council, and we're happy to share with you in the audience what they've been working on and learn a little bit about their company. So with that, Ashutosh, do you want to go ahead and take it away?
Sure, Terence. Thank you so much for that kind introduction. And thank you, everyone in the audience, for joining in and dialing in from all across the world. And I hope you had a great start to this new year. I am Ashutosh Singh, as Terence mentioned, co-founder and CEO of B Energy. And we are actually working on electrochemical graphene production process. So let's just dial into it and see what it is all about. Regarding what is graphene, why we use graphene, I would just simply define graphene for everyone, just to calibrate all the people in the audience about what graphene is all about. You can imagine graphene as a really thin layer of graphite, just a one atomic thick layer of graphite. And when you actually dial down the graphite to so thin layer, what happens is that it gains certain exceptional properties. And there's a huge list of exceptional increase in properties such as surface area, conductivity, and mechanical strength as such. So I think that really makes graphene an interesting specialized chemical product that really can add value to the industrial product like batteries and composite. For more information, you can go into the Graphene Council website and get some more information. Just a bit of more information about B Energy. We are, as Teres mentioned, we are a startup venture out of the University of Calgary. We are based in Calgary, so literally braving extreme cold weather to bring graphene to you, honestly. And we are working on a top-down approach. That means we take graphite as our raw material and convert that into graphene using electrochemical process. And we do also work on something called graphene membrane composite, where we try to sort of modify the membranes with the graphene to increase its performance. Going into the technology, as I mentioned, that it's an electrochemical process. What we really do is that we have two electrodes, one of them being graphite and another being a counter electrode, could be stainless steel or any other metal, which are usually exposed to a salt solution. And what happens is that the ions from the salt inside water are solvated with water molecules. So you can imagine these blue dots as ions in the salt. And when you apply current between these two electrodes using your power supply, what actually does is that it creates an electric field which actually pulls the ion between the layers of the graphite. And this process is called intercalation. So as the ions intercalate, you can actually see the graphite expanding through the reaction. And what happens as it completes, there is a water electrolysis takes place because they are not interacting by themselves with it. So these water molecules convert into oxygen. That creates a pressure between the layer, and that process, usually we call it as exfoliation, that pulls the layer apart. This is a schematic process to understand how this approach actually works. And what we found out that by doing this, we were able to save 70% more energy. And it was more energy efficient compared to conventional chemical methods. 70% more energy efficient. What I have here is a video demonstration as to how this process works, just to quench the scientific thirst of many scientific members in the audience. It's a school type demo that I want to play this for everyone and explain the process. So as we start the electrochemical process, so once you start the reaction, what happens is taking place. And if you carefully observe the graphite foil, you could see that its width is gradually increasing from what its initial thickness was. And this stage is usually what we call it as intercalation. And after a while, as the exfoliation propagates, you could see that the water associated with salt ions inside the layer starts to convert into oxygen molecule, creating a pressure between the layer, pulling the layers apart. And as we go forward, you can see more and more layer sort of moving up out of this graphite material. And so here you can clearly see that after like a couple of minutes into the reaction, you could see that the graphite is completely consumed in the reaction and you start producing a whole bunch of graphene. And there is also some unexfoliated graphite that has to be separated out. In all the chemistry that we work on and we have worked in the past, we observed a yield on the range of 60% to 94% with varying degree of quality. The highest yield at the chemistry that we have a IP around, we observed is 94%. Our total energy consumptions are less than 100 kilowatt hour per kilogram of graphene produced. So going to So during the course of this technology development, we observed several key benefits of this process. The first obvious one was the high quality product. And when I say high quality, quality in terms of the thickness of the graphene, since you are able to better intercalate under the action of the electric field, you are able to better control the intercalation process. And this process is able to ensure that you are actually peeling the layer more accurately. And hence you are able to generate more single layer, double layer, and triple layer graphenes. And that really brings the value to our customer or any other application development where they're looking for such kind of high quality graphene. Another advantage is that we usually control these experiments, and these experiments usually take less than an hour to complete, to completely consume the graphite in the reaction. In all of our chemistries that we developed, we actually used environmental friendly chemicals. So we don't really have any hazardous solution around, which requires a huge safety detailing to be done, or there is an issue of disposing hazardous chemical issues, something like that. So we usually use environmentally friendly chemicals. And we also have a slightly additional value in here. Since we are doing an electrochemical process, and during this oxygen evolution between the layers of the graphite, what really happens is that some of these graphene flakes get oxygen functionalized at the edges of the graphene flake. So if you imagine my palm as a graphene flake, the graphene oxidation happens at the edges. So you get certain oxygen functional group, which act as a so-called surfactant and make the graphene very nicely dispersed in water, which is really essential for several application development that we had conversation with our customers and partners. In addition to that, we also get certain heteroatoms doped into the graphene structure, which we will talk about in the later slides. Here are some information that our team collected on the thickness and lateral size information, which is really important. So for example, in one of the chemistries that we discovered and invented in our team, we found that we were able to produce a graphene of 1 to 2 layer, more than 80%, around 80% of the flakes were 1 to 2 layers, and with a lateral dimension of 1.67 micrometer. So we were able to produce really high quality material using that chemistry. And in terms of technical parameters, so our lateral size were 1.67 micrometer, 80% of our flakes highly dispersed in water were 1 to 2 layers. And because of that, we get a really high surface area. So the surface area we measured was 1,200 to 1,400 meters square per gram. And we had also observed that the electrical conductivity of these flakes were really high. So although we do oxygen functionalization, we do not completely oxidize the graphene. I just wanted to clarify that information as well. So we get a graphene which is functionalized at the edges, maintains its high electrical conductivity along with high surface area and very low thickness, a very high value add for application development, especially in lithium-ion batteries, for example, or any other high quality application, or for example, in membranes. Now, coming back to our tunability or flexibility in the operating conditions. So if we slightly change our parameter in the operating conditions, or if we change the chemistry, we are able to sort of dope in or bring in a separate heteroatom into the graphene structure. Allow me to explain. So we have carbon and oxygen, which is resulting from carbon, obviously, because of the graphene, and oxygen, definitely because of the functionalization. But in addition to that, we have sometimes nitrogen doped into the structure. And we can actually change it depending on the chemistry of the solution. Now, you might actually ask me, I mean, what is really going to add to us? So if you do a lot of electrochemistry, you would actually see that nitrogen in a carbon or a graphene heterostructure act as an electrocatalysis and can improve electrochemical reaction. Not only that, it might actually improve the electrical conductivity even better. So in certain cases, impurity might not be good, but in this case, although we are doping and nitrogen is adding impurity into the structure, but it actually is a good in some ways for our application development. And the great thing about this doping process is that it's not only confined to nitrogen. We can actually dope phosphorus, boron, sulfur, or a combination of these elements into our graphene structure as per our customer's need. And every specific functional group and doping has a specific application. So for instance, like we found out that some specific combination of this doping is really good for an anode of a battery, and specific combination of a doping is really good for a cathode of a battery operation, and vice versa. So these were a couple of information that I wanted to share on the tunability aspect, just to go in a little bit more deeper side. When we developed this technology or invention at the small lab scale side, we started to scale up. So there were several ideas around scale up design as to how we can scale up. So this was one of the design that we actually came up with, where we are actually doing several electrochemical exfoliation in a single reactor. So we have a couple of graphite foil along with several counter electrode. This is just a schematic. Here we just have two graphite foil, but we can have several of them depending on our graphene demand. And we have a salt solution of desired chemistry and depending on final product. And as we run through that process, what really happens is that the solution temperature starts to increase. So we have a heat exchanger that pulls the unnecessary heat out of the solution. And then we pump it back into the electrochemical system. So this is the scale-up design that our team is actually working on currently. And I'd like to show you how our reactor looks like. As I showed you in our schematic diagram, we have a reactor vessel, a feed reservoir, a heat exchanger, and a feed pump. So we actually have most of the electrochemical reaction really happens in the reactor vessel. We have certain proprietary information as to how we do the electrochemical electrode distancing and other information. And we carry out in reaction in this electrochemical vessel using those data. And then we actually sort of circulate the electrolyte to pass it through the heat exchanger to pull the unnecessary heat out, because the electrolyte temperature really increases to quite a high temperatures. I mean, in certain instances, water starts to boil. So that is a level of heat that is usually generated in this reaction. In terms of process detail, at this moment, what we are really doing is that we have a raw material. We take the graphite raw material and we do the electrochemical processing and we produce functionalized graphene that has a really high electrical conductivity. And we pass this on to our customers or partners for application development. For example, it could be a lithium-ion battery where we can really add value. It could be a membrane application development that we are presently also working on. But as we go into the future, we are also kind of thinking about value-added products. So one of the aspects we are actually working on is the graphene-coated membranes. And this was really interesting because we took a conventional membrane and coated it with our graphene. And what we observed was that there was a significant improvement. Now, I know many people are asking me, probably might be thinking, what does significant mean? So more than 50% increase in the power density of the redox flow battery. We think it's because of the layer being so thin that it's being very selective to just H plus ions, and it's reducing the crossover. It's also doing a bit of electrochemistry in there because of the presence of heteroatom. And we could see that it was adding value to those sector as well. So these are a couple of graphs. Since we are at the initial stages, we are sort of expanding our product portfolio at the moment. We have two ready to take off-the-shelf product at the moment, which is basically the graphene powder form that we are producing, and in the suspension form, depending on the concentration of the customer. But if there is any other specific form that you probably might need graphene in, please do let us know. Please get in touch with us, and we will try our best to sort of make that happen for you. It could be graphene film, for example, or a graphene coated membrane. We can make it happen. I do have a small announcement to make in this presentation on this platform. And this is for academic researchers or for especially working in universities, national lab, government laboratories. If you do need graphene, we are opening our sales for R&D development by the end of January, and they are available to order. Please do directly get in touch with our team, and we will be able to sort of give you more information on that. With that, I think we are just almost coming to the end of the presentation. We have an innovative graphene manufacturing process, unique chemistry, producing high quality, bringing in value for our customers in terms of time, and bringing flexibility in terms of functionalization, highly dispersible functionalized graphene with maintained electrical conductivity and very thin. And our team also has electrochemical and material science expertise to make this happen. With that, I would like to thank you all for joining in from all parts of the world. And I would definitely like to thank Terence for giving us the opportunity to present on this platform. And please do get in touch with us. My email ID is on your screen as I'm sharing it. So you can please get in touch with us. Thank you. Thank you, Terence.
Thank you, Ashutosh. Thank you very much. And Ted, I don't know if you want to join in. There you are. There are a number of questions, and I want to first acknowledge this. I think I appreciate that you're kind of exposing what you're working on, how you do this, which is great because not everybody shares what they're working on and how they make graphene. I have a couple of my own observations. One is, on the surface of it, the process seems quite simple. Right, it's a piece of graphite and applying an electrical current and doing the intercalation, et cetera. But I think what's important, and I don't know if there's a direct question about it, but that's what prevents people from just copying what you've done, and where is the secret sauce, and how do you protect your IP? Can you talk a little bit about that? What makes this different? What is defensible from a business point of view, and how you protect your intellectual property?
That's a very good question, Terence. I will just go first, and probably Ted might also be able to add a couple of more information. So there are many things that we have sort of in the process, especially around the chemistry, the chemical we use. That's an important aspect. Secondly, the pH we operate at, the temperature, and other operating parameters such as cell voltage, current density, and how those electrodes are arranged. So we have a proprietary information around that as to how we do that. In addition to that, Terence, it just hit me. Our team also has something what we call as processing parameter map. So we can actually tune in those processing parameter and produce a specific graphene for our customers that our customer could use. That is something we actually protect. So I was able to answer the list.
Yeah, I think to add my comments. I think the key is in the composition of the solution that you work with and the electrochemical conditions, and that's what we try to keep confidential, or the secret sauce, as you say, for us. The concept of electrochemical exfoliation is quite widely studied in the academic literature. So there are a few different methods that are out there. The method that Ashutosh has developed, we believe gives us a better quality product and a low cost production, relatively low cost of production.
Excellent. Ashutosh, if you don't mind, maybe you could stop sharing the screen and then it'll just show us, because I don't think we need to go back to the slides for some of these other questions that we have. There, that's better. So
Thank you,
more of us just like on a panel. So I'm not going to take these questions in any particular order, but we'll address. We've got quite a few, which is great, and we want to make sure we answer all of this. So one of the things we didn't see in the presentation and there's a question about it, is the post-processing steps. How do you separate out the graphene from the larger particles? And before you answer that question, I do want to make a statement to everybody who's online, because we didn't mention it. The Graphene Council has actually tested and characterized this material. So we've actually had hands-on, eyes-on this material. And I will make this comment. From the Graphene Council perspective, we never really talk about good quality versus bad quality graphene. It's always a certain type and form of graphene is better suited for certain applications. Having said that, there is not a lot of multi-layer graphene out there that is primarily in the 1 to 2 layer range. Most of it is 5 layers, 6 layers, 7 up to, and according to ISO standard, it's up to 10 layers. So I just want to acknowledge that through our testing services, which the Graphene Council offers, we have fully characterized this material, and we have received the same parameters that you have seen displayed here. And it is fairly unique in the sense that there's not much material that's actually 1 to 2 layer. It's usually more than that. So now coming back to the question, when you're producing this, is how you then get to that material and separate it out from some of the unprocessed parts of it and everything else. Can you talk about that filtering process?
Certainly, Terence. So that's a very good question. So in the lab scale, when we were developing this chemistry, we were often using centrifuge to sort of separate those graphite from graphene. Recently, our team has sort of come up with an innovative process to sort of get rid of the centrifuge process. And we are sort of scaling up that innovative process at the moment. But there is quite a bit of idea within our team. So for example, the chemistry that our team working on giving us a yield of 94%. The question is, do you really want to do centrifuge for that? Because we're producing so much graphene in there, it's most of which is just graphene. Do you want to put in energy to remove 6% of the material? So this is something we are actually working on. Ideally, for a premium quality product where the read is like pure graphene, we want to centrifuge them and get it to our customer. So yeah, on the post-processing side, that's what we are doing. We also do a bit of sonication, just so that we get a uniform distribution of the graphene in the sort of medium whichever our customer needs, mostly water. Yeah, that's all I can say on the post-processing side.
Okay.
Yeah, I'll just add something to that, Terence. From the academic side, we're always making tiny milligram quantities, usually on the bench scale. But we've been thinking a lot about the scale up. But we're at an early stage. I'd say we're producing at the moment sort of gram quantities, but that's still a lot for us to be able to produce. And so we're scaling up our filtration and washing steps. We want to get to the sort of kilogram scale, but at the moment we're at the sort of gram scale. Beyond that, the separating the graphite, I think that's a challenge, as you say. The centrifugation is the standard method that's used in academia. Scaling that up can be challenging, but it's possible. And then the other thing I wanted to emphasize is that we don't do any chemical reduction of our product. We produce a graphene product directly. I know you can make what is graphene oxide and what is graphene? It's actually a spectrum. And so there is some oxidation, of course, of the graphite during the process, but it's relatively low, as you saw the carbon-oxygen ratio is up to 15, depending on how you measure it. And we also have quite a bit of functional groups on there, which may be, we have some ability to tune that depending on the conditions we operate at. I have been answering some of the questions, Terence, in the Q&A, but there's a lot of them have come in, so I haven't been able to get to them.
It's fair. I can't remember the last session we had where we had quite so many questions. Obviously, everybody's quite interested in the technical side. Maybe just to comment on the oxidation level. Again, from the Graphene Council perspective, we see a lot of material. We see everything, right? With having that small, 7% oxidation on there can actually be quite positive. Again, there's some material out there. Graphene oxides tend to be more in the 30-35% oxygen content, and then they're clearly in a different class and application area. The graphene nanoplatelets or graphene particles that have no oxidation, that's another. Having slight oxidation on the particles does lend itself to particular applications, as Ashutosh, as you referred to in the session. And so I mean, just from our perspective, 2 cents, I'm not sure why you would even want to reduce it. You'd actually, in some cases, want to have that oxidation on there.
Yes, Terence, yeah, please.
I'm going to just move ahead kind of quickly, just because there's so many questions. Otherwise, we'll never get to them. On the first statement you made about the 70% reduction in energy, of course, people would like to know compared to what? What did you compare the energy consumption to?
That's a very good question. Since we are in the exfoliation world and there is a huge amount of spectrum how you can produce graphene, what we produce is exfoliated graphene, and hence we compare it to the chemical method of exfoliation as our gold standard. Yes, Terence.
Okay, understood.
Just to add something on that, of course, there are a lot of different processes. So that was based on a paper we found with an energy analysis. So yeah, we at some point, I guess we should put together our figures as to what the actual. I think Ashu had some figure for the energy consumption of our process per kilogram of product. And so, that's probably a more sensible way of displaying it, I guess. But from what we've seen, we think that the energy cost is not a big part of the cost of production.
Excellent. There are a bunch of technical questions about, how the measurements were performed and such as that. And what I'd like to suggest, all of these, anybody if you put your question in the Q&A dialog box, the questions are captured. So we will be able to answer them. I think what we might do is we should take all these questions, Ted and Ashutosh, and then maybe put together a written response to this that we can then distribute to everybody, because there's quite a few. On the testing methodologies, I will speak just briefly that the Graphene Council has put together something called the Graphene Classification Framework, which has been licensed to ISO to turn it into an international standard. And within that, we have the measurement characteristics for layer count, chemical composition, etc. And there are best practices on what test methods are used for each of those. So that's something we could spend a whole day talking on just on that. And I think we should come back to that. There was a question about if you had any AFM images or TM images or something on how to verify the layer count. I know when we did the testing for you, some of the methods we use include, of course, Raman spectroscopy, but also SEM and TEM imagery. Do you have a technical data sheet, for example, if somebody wants to know about your product and see these specifications, including the optical spectroscopy? Is that something you can provide for them?
Definitely, Terence. That's a very good question. We have a detailed analysis of the AFM. I think we did also statistical analysis. So we did not just sort of evaluated a couple of flakes. We evaluated a bunch of thousands of flakes or so, and then did a statistical analysis on those to sort of arrive at a conclusion. So short answer to your question is yes, we can definitely provide all the information on the flake size, flake thickness, AFM and TEM data that we have and that we received from the Graphene Council veterans.
Yeah, just to comment on the technicalities, because I know we've got some academic people here, determining the number of layers, a lot of the literature uses AFM. The problem with AFM is it gives you a thickness. It doesn't tell you how many layers you have, and you have to interpret that. And the thickness. So AFM is a little bit tricky because your actual depends on what force you apply, whether you've got functional, whether you've got adsorbed water, whether you've got functional groups there. What is your substrate? Is there a gap between the substrate and the graphene? So really knowing what you've got with AFM is a bit uncertain, I would say. Working with Terence's team on the analysis and using TEM to get data on number of layers is what we believe are better. Consistent.
Yeah,
if you're from the technical side, I think we're pretty confident with what we have.
It sort of worked out for us. Yeah, I would say yes. I agree.
Yeah, I would echo that in terms of the AFM and the problem you have with sample prep, selection bias, which flakes because you can only test a smaller number of flakes, and et cetera. It does cause quite a bit of problems. The other method that has often been advocated is to use Raman spectroscopy and interpret some of the signals for the layer count, but that is also fraught with a high degree of uncertainty. Raman's good for the sp2, confirming the sp2 presence, sp2 bonded carbon, but we don't recommend relying on Raman for layer count, even though you need really more like the CVD type graphene or true monolayer material, and then you can use that kind of method. So on the commercial side, there's a couple of questions related to the commercial aspects I want to ask you guys. One is, when do you anticipate maybe reaching commercial production capacity? And the other related to that is, are there any particular target markets that you've identified that you think are the most commercially viable for you?
That's a very good question again, Terence. And I think on the scale-up side, so our team is presently working on targeting 2 kilogram per day production. We are sort of anticipating that to complete by April end. So we're sort of into that, almost completing it. So hence we decided to sort of launch our R&D sales for those products, since we are in that range of 15 to 20 gram per day production at the moment. Given the high quality of our graphene material, I would say from the customer engagement and discussions I had with several people, I would say lithium-ion battery is the best target market for us. We can really add value to that. And some other sectors, for example, membrane was another one where it sort of emerged that our graphene could add a huge amount of value. It's not only because of graphene being very ion selective towards H plus ions in the membrane, but it's also because our graphene has certain heteroatoms doped into it. So it's sort of improving the electrochemical reaction within the battery. Then customer can kind of play around with that improved performance. They can reduce the size of the battery if they want to, or probably increase the capacity or power density of their system. So those are the couple of areas at the moment that we are pursuing, Terence.
Excellent.
I just want to add for the production scale, as you know, from trying to commercialize something that's coming out of the university, it's hard to predict the timeline, and it depends upon a lot of factors. But where we're at is that small scale production right now. We will need some investment to go to scale up to larger scale to industrial scale production. And so what the timeline of that is will depend. I think for the target markets, we are looking for that high value, low volume for that early stage opportunity for us. But I think also our product will be applicable to those high volume applications like composites and coatings and other things. I think, with that 1 or 2 layer material, as you say, if we can produce it at the right cost for those large volumes, then I think there are also opportunities there. But I think that's a bit longer term for us.
Yeah. Well, again, we, as the Graphene Council, we love all our children equally. We're very neutral on all of this. But we have collected and evaluated 600 different TDSs of commercially available graphene. And I would say something with the combination of primarily 1 to 2 layers, so 80% of it in that 1 to 2 layer count distribution, and with the slight oxidation, should be a material of interest for a lot of people. There are a couple other materials that have existed in the marketplace, but I would say you can count on your hand how many. And so I think this would be an interesting material for consideration. There's another question or a couple of questions that relate to the raw material used. The question, and there's another one that's actually related on the other end of the process, and it goes along the following. How critical is the purity of the raw material you use? Is there anything special about the graphite foil you use? Could you use some other carbonaceous material like a very high carbon content coal material, which is, converting coal to graphene is of intense interest in many parts of the world today. And then another related question, sorry to bunch all these together on you, but the other related question was about contaminants or other residues. You gave the, 93% carbon, 7% oxygen, 0.5% nitrogen in one case, something like that. But obviously, junk in, junk out, if you have contaminants in the raw material, they're likely to end up on the other end of the process. But just talk to us a little bit about how important it is on the raw material input. Is there anything special about the graphite that you're using in particular? And what about contaminants, residue, or any unwanted material that you're ending up with, if any?
Sure, Terence. So on the raw material side, in the video demonstration that I presented, we actually use graphite foil, and we still use graphite foil at the moment. The graphite foil, just to calibrate all the audience to the same level, is a specialized process version of the graphite that is extracted from the mines. So you get that sort of a film or sort of a three-dimensional electrode, which you just attach it to the clips and do the reaction, rather than graphite powder. So,
sorry, Ashutosh, but
yes,
this is simply commercially available,
yes,
widely available graphite foil, which is often available as a heat spreader or some other tool, right?
Yes, you're correct, Terence. Yes, I was just about to say that as well.
Okay.
So these are commercially available graphite foil, and they are really available at a standard purity of 99% in the market, which is what we usually buy. And even after using that, we are able to sort of, they do not present a huge cost for us. And going forward, we have another plan to sort of use the powdered graphite from the mines into a reactor. So we have a specialized reactor design to use powdered raw material to sort of produce graphene from that. We're working on that design as well. That will really reduce the cost on the raw material side. I'm just.
Can I add something, Ash?
Yeah, Ted. Allow me to sort of
complete.
Allow me to sort of, because I'm kind of organizing my thoughts around the coal to graphene. That's a really interesting idea. We had exactly similar idea. Coal to graphene is really, I like that idea, but we had an idea around bitumen to graphene. So if you come to Alberta, we usually have a lot of bitumen around here, which is sort of a waste product coming out of the oil and gas industry. So I think me and Ted were discussing how about we use that as a raw material instead, and see, we can produce that as a high value graphene out of that. So that is probably longer term innovation that probably our team would sort of focus on. At the moment, we started trying to focus on graphite foil, getting this done, and then moving on to the graphite powder. And in a longer term, we probably might consider coal to graphene, bitumen to graphene, another aspect. Yes, Ted, please go ahead.
I just want to say, for me, I think the purity question, it depends on your application, right? But so, if you're making battery electrodes, you're probably more concerned about impurities than you are if you're making concrete. And well, I don't know, maybe, but anyway, I think it depends on the application. And I think, for those high value applications, you're going to be willing to pay for the higher quality raw material. And having said that, I think graphite powder is a lot cheaper than graphite foil, and we've already demonstrated in our lab that we can use this process with graphite powder. And it doesn't, the cost matters, but it's not critical, I would say, for those high value applications. It's for the large volume applications where I think we need to push that lower cost raw material. In terms of using wastes, or coal, I think it's fun and interesting, but whether it's commercially sensible or not, I'm not sure. I'm personally not convinced. because the amounts you're going to use are quite small. And so, if you really don't care about the quality, the impurities, then sure. But if you do, then it might not be worth the risk, I would say.
Yeah,
that's just my thoughts on the matter. But
no, that makes sense. And speaking of bitumen, by the way, we did and are continuing to test graphene added to bitumen for asphalt composition, and adding graphene does have a positive impact on that. So that might be a nice high volume, but of course, very low price market. I think this just speaks to the fact that graphene can be used in so many different ways. And there are going to be many different markets depending on what the particular requirement is. And they'll be at all ends of the spectrum in terms of expensive from cheap, high volume to low volume, that sort of thing. I have another question for you guys, and I think then we'll kind of wrap this up. And then we'll come back and address maybe some of the questions we didn't quite get to, because there's almost 50 of them now. The question on the commercial side is, what is the roadmap on commercialization? Are you looking at potentially licensing this technology? Are you looking to expand? And then, of course, you have some graphene companies that look at vertical integration, where they not only make the graphene, but then they make either an intermediate or even an end use product. Can you speak a little bit about what the commercialization strategy is for that?
Sure, Terence, thank you. So we are actually sort of at the moment, since we are at the initial stages, we're sort of producing those powder and suspension for research and development sales. As we move forward, what we are probably looking at is trying to develop certain graphene-based products. One of those things was graphene-based membrane, where we got a huge amount of interest from flow battery community, but there are other membrane users that are interested as well. So these are a couple of things on the commercial strategy that we are looking at. And so I see, particularly for myself, B Energy as something like a graphene-based product developer. Yeah, in the short term, yes, we are sort of selling graphene into markets. But I guess, when we sort of develop the product, we move up the value chain. So I see that as a trajectory for B Energy, and sort of going into that area. Yeah, Terence.
Excellent.
Licensing, we really hadn't had so much discussion about licensing because we haven't thought about it at the moment. That is what I would say. It's a great opportunity and we are open to it, but we want to sort of look into what it's there for us in that. Yeah. Yes,
yeah. Those are two obviously extremely different ways of going to commercialization. And each has their set of pros and cons, but I think the product development does give a company a little bit more control. And, I think you also get higher value for the graphene you produce when you get it into an end product. Ted and Ashutosh, I want to ask you, before we maybe conclude here, did you guys see any questions in particular that you wanted to address that we haven't talked about yet? Or last comments you want to make?
So there was a question about scalability, and we haven't, we talked about the fact that we are scaling up, but I just want to comment on scalability. So electrochemical processes can be scaled up to very big scale. Chlorine production is an example of an electrochemical technology that's at big manufacturing scale. I'm an electrochemical engineer. That's my background. And so I've worked on a scale up of a lot of different electrochemical processes. There are challenges in scaling up electrochemical processing. You need to have the right expertise to be able to. One of the strengths of our company that we have expertise in-house already. And so, I think part of what our company will have in terms of IP is both the secret sauce, but also the know-how to scale up. And so, yes, there are some challenges, but there's no reason why we can't produce this at any scale you need. A preliminary analysis of the scale up to produce a ton a day is a small lab actually is big enough to be able to produce that amount of material. There are, like I say, some challenges, some of the electrical engineering stuff that we will need to make it scalable, but there's no fundamental reason why it can't be scaled to whatever scale you need.
Excellent.
I just want to add to Ted's, sorry, Terence, I just want to add to Ted's comment because, our team, and especially Ted, has worked on chloralkali process, electrochemical process in the past. And I particularly Back in the days in my undergrad was really working on chloralkali, and there are other electrochemical systems that I've worked on. So as Ted mentioned, our team has electrochemical expertise to sort of scale this up. And electrochemical systems have scaled up in the past without any problem. So yeah.
Yeah, it would seem that there aren't any real significant hurdles there that couldn't be overcome. And of course, a little bit of capital goes a long way to helping address that, right? A little bit bigger kit.
Yes.
Well, listen, from my side, I really appreciate you guys being so open and sharing, what your process is about, where you're at in this stage of development, and just showing what you guys are able to produce. And I want to repeat again, I think it's important that you've had your analysis, you've had third-party testing of it, and the Graphene Council has actually tested your material. And so we've been able to see what it is you produce. And so that's, I think, important in this field of graphene, that people can deliver the receipts, so to say, on what they claim to be able to produce. Any closing comments from either of you or both of you before we conclude today's webinar?
Terence, as you said, there are a lot of questions on there, and we would like to go through and produce a written response where possible. And of course, anybody can reach out to Ashu and I to answer any specific questions, and we will share. We can share some definitely details, images of the product or whatever else it is about the product. We can certainly share more details with people who've asked for that. So yeah, apart from that, I think good job, Ashu. Well done.
Thank you, Ted.
So from my side, let me just say thank you, Ashutosh. Thank you, Ted. Appreciate you guys being a member of the Graphene Council. Thank you for sharing this information with everyone. For those of you watching this presentation, thank you for your interest in it. And if you do have general questions about the Graphene Council, want to learn more or get engaged with us, please reach out. That's what we're here for. And with that, I want to wish everyone a great rest of your day, and thank you. Take care.
Thanks, buddy. Thank you, Terence. Thank you, Ted, for joining.
Thanks, Terence. And thanks to all the good questions too.
Yeah.
For more information and to connect with expert partners, contact the Graphene Council at thegaphenecouncil.org.